Who do you take your life advice from? Will a kid's opinion suffice? The answer is usually no. But what if the child understands much more than you do about what's actually happening? Think it out carefully, and then you will realize that kids' potential shouldn't be ignored. There are countless brilliant young people in this world. There are kids like Malala Yousafzai who do phenomenal work and gain international recognition for inspiring acts. At 21, Elizabeth Nance worked at Johns Hopkins to develop nanoparticles to penetrate brain tissue. Brilliance knows no specific age, and truly gifted ideas are often rewarded. But then there are kids like Max Laughlin. Max Laughlin isn't just any kid, though. He is the smartest one in the world. At the age of 13, he was behind the invention of a free energy device, which is a technology that might power the entire world for free. He's famous worldwide for his brilliant ideas, along with his point of view on topics such as alternate realities and the nature of the universe. And recently, Laughlin once again made waves with a jaw-dropping revelation about CERN. In the words of Laughlin, the largest particle physics laboratory in the world could have destroyed the universe, and we actually live in a parallel universe that was the closest to it. But what are the arguments and the science behind his portal? Join us as we dig deep into top secrets of the world's most controversial research facility. The European Organization for Nuclear Research, known by its French acronym CERN, is the largest particle physics laboratory in the world. Located just outside of Geneva, Switzerland, it was established in 1954 as one of post-war Europe's first joint ventures, with the express aim of halting the brain drain of talented scientists leaving the continent for America. Today, more than 10,000 scientists, hailing from more than 100 countries, find themselves at CERN each year to use its facilities, which include some of the biggest and most complex scientific instruments ever created. Their goal: figure out what the universe is made of and the laws of physics that dictate its behavior. So, if you see a news headline about exotic new subatomic particles, the chances are the discovery was made at CERN. An example occurred in January 2022 when CERN scientists announced evidence of X particles in the quark-gluon plasma. Hiding behind that technobabble is the eye-popping fact that CERN had succeeded in recreating a situation that hasn't occurred naturally since a few microseconds after the Big Bang. That particular study drew on pre-existing data from CERN's Large Hadron Collider. The Large Hadron Collider, or LHC, is the world's most powerful particle accelerator, a giant machine that physicists use to smash tiny subatomic particles together at extremely high speeds to see what happens. The particle collisions recreate, for a fraction of a second, the conditions that existed moments after the Big Bang, when the universe was born. By studying the debris of these collisions, physicists try to settle mysteries such as what matter is made of and how particles get their mass. The LHC, which was completed in 2008, was built primarily to put the standard model of particle physics to the test. This wildly successful theory from the 1970s describes the interactions between the 17 elementary particles and 3 of the 4 fundamental forces of the universe: electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity is the 4th. The standard model long predicted the existence of a never-before-seen elementary particle called the Higgs boson. After 4 decades of searching, in July 2012, physicists finally found it using the LHC. The discovery was a big win for fans of the standard model, but the theory is incomplete. It leaves many questions open, such as, what is dark matter? Why does the universe contain more matter than antimatter? The LHC may help answer these questions. The machine is buried deep underneath the France-Switzerland border near Geneva, in a circular tunnel nearly 27 kilometers long. It uses more than 1,035-ton superconducting dipole magnets, cooled to a temperature of 271.3 degrees C. colder than outer space, to guide two beams of particles, usually protons, in opposite directions around the ring. The protons race around the 27-kilometer ring at almost the speed of light, completing over 11,000 laps per second. At 4 points around the ring, the two opposing beams are steered so that they cross paths. Where the beams intersect, the protons within them slam into one another and shatter into smaller particles. Most of the particles produced in the collisions are highly unstable and decay into more stable forms almost instantly. 7 enormous detectors, think of them as cathedral-sized digital cameras, are built around the 4 collision zones to capture data about these incredibly rare particles as they blaze briefly into existence. The LHC was initially switched on in September 2008, with a plan to run for at least 2 decades. The plan includes a handful of long shutdowns where the machine is turned off so that scientists can access the equipment, perform repairs, and make upgrades that allow it to operate at higher energy levels, which means more potential discoveries during the following run. And as told, by simulating conditions similar to the Big Bang, scientists at CERN used the LHC to explore the fundamental building blocks of the universe. However, the LHC has not been immune to controversy. Since its conceptualization, fears have been raised about its potential to create a doomsday scenario, with fears that the new atom smasher would destroy Earth, perhaps by creating an all-consuming black hole. Even Francesco Calogero, a Nobel Peace Prize-winning nuclear physicist, published an article in the early 2000s questioning whether a laboratory experiment could inadvertently bring about the destruction of planet Earth. These concerns were widely debated and even discussed on renowned television shows like John Oliver's Daily Show. However, the scientists at CERN have refuted these claims, asserting that the LHC is designed for scientific inquiry and not as a doomsday machine. Regardless, the concerns surrounding the Large Hadron Collider's destructive still capabilities have persisted for years. Prominent among those who support the apocalyptic scenario is Max Laughlin. The young teenager has been labeled as a genius, but no one can really trace back who started the name other than Laughlin's own parents. Laughlin made waves when he developed this completely real energy device that should give the world infinite power. And that's where the first problem in this story begins. Why have you never heard of such a device, you ask? You have to pick one of 2 theories. 1. The device never actually worked, nor could it be upscaled into any sort of efficient manner. 2. Your government personally made sure that you would never hear of Max Laughlin or his incredible free energy device. What do the smart adults believe? Why isn't the Max Laughlin free energy machine working in your home yet? While most blogs that talk about Laughlin's genius would recommend the latter reason is true, Laughlin himself might have, you believe, it's a totally different reason. Maybe it's a result of the Mandela effect. Never heard of it? It's the universal excuse for forgetting things that now have a pseudoscience following. Paranormal researcher Fiona Broom coined the name in 2009 after becoming convinced that then South African President Nelson Mandela had died in prison in the 1980s. But Mandela did not die in prison. He was released in 1990, went on to lead South Africa, and died in 2013. However, Broom noticed that many authors seem to share the same inaccurate memory, prompting further investigation. Since then, more communal false memories have surfaced, such as C-3PO of Star Wars fame being entirely golden while he has a silver leg, Jiffy as the name of a well-known peanut butter brand, but it's just Jif, the spelling of a classic children's book being the Berenstain Bears, it's really the Berenstain Bears, and a host of misquotes from movies, among them Luke, I am your father from The Empire Strikes Back. The actual line is, no, I am your father. If you build it, they will come, from Field of Dreams. It's, if you build it, he will come. And perhaps the most misremembered of them all, Mirror, Mirror on the Wall from Snow White and the Seven Dwarfs. The Wicked Queen actually says, "Magic mirror on the wall." But why do so many people misremember these? Well, in the words of neuroscientist Wilma Bainbridge, an assistant professor in the University of Chicago's Department of Psychology, the Mandela effect is a really fascinating memory phenomenon, where everyone seems to show incorrect memories for common popular icons. It is really growing in popularity on the internet on sites like Reddit and TikTok. And while for many people it's sort of a fun little game that they might play, I realized that it is actually a very interesting effect of human memory that hadn't been studied experimentally before. With co-author Deepasri Prasad, Bainbridge conducted a rare study published by the journal Psychological Science in late 2022 on the Mandela effect, in which they first confirmed that people have confident but incorrect visual memories of famous icons or characters. Prasad was a lab manager and research assistant at UChicago at the time of the research, and is currently a doctoral student of psychological and brain sciences at Dartmouth College in Hanover, New Hampshire. The researchers tried to find simple causes for the phenomenon, such as people not looking directly at the detail in question when observing the character or images across the internet displaying the errors, but they found no match for these hypotheses. Bainbridge and Prasad also had the participants in the experiment draw the icons from memory to see whether they would spontaneously create these errors, and they found that they often did. Eventually, their paper described an empirically observable phenomenon that persisted across people with no clear explanation. Where things get difficult is when people suggest that CERN, an organization that studies physics phenomena, is cast as potentially causing those phenomena. A mix of conspiracy theorists, researchers like Cynthia Sue Larson, the author of Reality Shifts and Quantum Jumps, and regular people have been searching for an explanation for this collective cognitive dissonance and false memory for decades. The current leading theory among a subset of true believers is that Mandela effects are evidence of multiple timelines, universes, ripping of space-time, or another physics phenomenon. The thinking here is that there actually was a movie called Shazam for a specific subset of the population who lived in one universe or version of reality, and those people have somehow either collectively switched realities or reality itself has shifted, and a certain subset of the population has a collective memory of what things were like in the before times, when it was Looney Tunes instead of Looney Tunes, for example. As Larson said, "I've had the great good fortune to witness thousands of reality shifts and Mandela effects, including some that have flip-flopped or gone first one way and then another, which has led me to contemplate that, as physicists Leonard Susskind and Raphael Bousso suggested, the many worlds interpretation and the multiverse of eternal inflation are one and the same thing. The thought among at least some in this space, including our world's smartest kid, is that CERN's Large Hadron Collider, which has helped us discover and verify an astounding amount of new or theorized information about subatomic particles, physics, and the nature of the universe, is somehow causing these reality shifts. Max Laughlin has a theory that the largest particle physics laboratory in the world could have destroyed the universe, and we actually live in a parallel universe that was the closest to it. The Mandela effect lends support to Max's hypothesis that we may be living in an alternate extension of our universe. According to Laughlin, these alleged openings of portals at CERN imply the existence of adjacent universes, with the Mandela effect acting as evidence of our transition between realities. While Max Laughlin's claims made waves in social media networks, we're still here in 2024, and though it can sometimes feel like we're living in a hellscape, we are, at least for the moment, still a pre-apocalyptic society. And the LHC was restarted after 3 years of maintenance work and upgrades on 22 April 2022, allowing protons to collide once again. This period is called Run 3. Notably, at this time, the International Large Hadron Collider Beauty, or LHCb collaboration at CERN's LHC, has made a groundbreaking discovery. They unveiled the existence of 3 unknown particles, adding to the ever-growing list of exotic hadrons found at the LHC. 3 never-before-seen particles included a new kind of pentaquark and the first-ever pair of tetraquarks, which includes a new type of tetraquark. The findings, presented at a CERN seminar, add 3 new exotic members to the growing list of new hadrons found at the LHC. They will help physicists better understand how quarks bind together into these composite particles. Quarks are elementary particles and come in 6 flavors: up, down, charm, strange, top, and bottom. They usually combine together in groups of 2s and 3s to form hadrons, such as the protons and neutrons that make up atomic nuclei. However, more rarely, they can also combine into 4-quark and 5-quark particles, or tetraquarks and pentaquarks. These exotic hadrons were predicted by theorists at the same time as conventional hadrons about 6 decades ago, but only relatively recently, in the past 20 years, have they been observed by LHCb and other experiments. Most of the exotic hadrons discovered in the past 2 decades are tetraquarks or pentaquarks, containing a charm quark and a charm antiquark, with the remaining 2 or 3 quarks being an up, down, or strange quark or their antiquarks. But in the past 4 years, LHCb has discovered different kinds of exotic hadrons. The discoveries announced recently by the LHCb collaboration include new kinds of exotic hadrons. The first kind, observed in an analysis of decays of negatively charged B mesons, is a pentaquark made up of a charm quark and a charm antiquark, and an up, a down, and a strange quark. It is the first pentaquark found to contain a strange quark. The finding has a whopping statistical significance of 15 standard deviations, far beyond the 5 standard deviations that are required to claim the observation of a particle in particle physics. The second kind is a doubly electrically charged tetraquark. It is an open charm tetraquark composed of a charm quark, a strange antiquark, and an up quark and a down antiquark, and it was spotted together with its neutral counterpart in a joint analysis of decays of positively charged and neutral B mesons. The new tetraquarks, observed with a statistical significance of 6.5 doubly charged particle and 8 neutral particle standard deviations, represent the first time a pair of tetraquarks has been observed. According to LHCb physics coordinator Niels Tuning, the more analyses we perform, the more kinds of exotic hadrons we find. We're witnessing a period of discovery similar to the 1950s, when a particle zoo of hadrons started being discovered and ultimately led to the quark model of conventional hadrons in the 1960s. We're creating Particle Zoo 2.00. While some theoretical models describe exotic hadrons as single units of tightly bound quarks, other models envisage them as pairs of standard hadrons loosely bound in a molecule-like structure. Only time and more studies of exotic hadrons will tell if these particles are one, the other, or both. Scientists believe that there are some major mysteries in the universe that scientists hope to answer, and the LHC could be instrumental in some of that progress. Let's explore 10 strange corners of the universe that the LHC could explore. The Higgs boson. What is probably the most famous discovery to come out of the LHC to date, the Higgs boson, is an elementary particle the existence of which was confirmed in 2012 at the LHC. There is, however, still a lot to be learned from studying the strange particle. First proposed in 1964 by a group of theorists including Peter Higgs and François Englert, the Higgs boson was the last undiscovered particle predicted by the Standard Model, the theory that explains all known fundamental forces and particles in the universe. In 2013, Higgs and Englert were awarded the Nobel Prize in Physics following the LHC's detection of the Higgs boson the year before. The Higgs boson was suggested as an explanation for why certain particles have mass. The particle is associated with what is called the Higgs field, which gives mass to other elementary or fundamental particles like electrons and the quarks that make up protons. The particle even gets its own mass from interactions with the Higgs field. But not all fundamental particles have mass. The photon, or light particle, has no mass, for example. There remain many mysteries about the Higgs boson, and with future experimentation at the LHC, particle physicists could paint a more complete picture of this strange particle. LHC scientists have already observed the Higgs particle doing strange things ever since they finally spotted it, offering additional mysteries to solve. In fact, in Run 2 at the LHC, researchers experimented to see if the Higgs boson might decay into dark matter particles, though they did not detect this. Dark matter. Scientists hope that with the help of the LHC, they will be able to find particles that constitute dark matter, the never-before-observed stuff that makes up about 80% of all matter in the universe. Dark matter is a mysterious material that scientists predict makes up over 80% of all matter in the universe. Although dark matter is invisible material of stars, planets, and galaxies. In other words, we can't see dark matter, but we know it's there because we can see its effects. Currently, scientists have a number of different dark matter candidates, strange particles that could be the elusive dark matter. But while the culprit hasn't yet been identified, the LHC remains a powerful tool that scientists will continue to use to solve this major mystery. Like CERN officials wrote in a statement, if the LHC detects a potential dark matter particle, it will require confirmation from the other experiments to prove that it is indeed a dark matter particle. By contrast, if the direct and indirect experiments detect a signal from a dark matter particle interaction, experiments at the LHC could be designed to study the details of such an interaction. Dark energy. While its name might seem to imply that dark energy is similar to dark matter, their connection lies in the name alone. In addition to their similar names, dark energy is also invisible and expansive. Dark energy is a mysterious force suspected to make up nearly 3/4 of the universe, and scientists think it's causing the expansion of the universe, is speeding up. While the LHC is designed to experiment with particles, some theorists have suggested that if dark energy is a type of force or field, then the LHC could be used to investigate that idea, similarly to how the LHC used the Higgs field to produce the Higgs boson particle, physicist Claire Burridge described to Symmetry magazine. Cosmologists know that there is new physics we don't understand, and all the evidence is pointing towards something very fundamental about our universe, Burridge said. The experiments on the LHC are also very interested in the fundamentals. Scientists have also suggested that dark energy, if it's a type of field, could produce lightweight particles, Burridge said. The main focus of LHC has been heavy particles, so we had to go back and reinterpret the data to look for something light, she added. Wimps. In terms of dark matter, one of the candidates that's gotten serious attention over the years has been weakly interacting massive particles, or WIMPs, which LHC has already investigated. WIMPs are hypothetical particles that are said to interact via forces including gravity and which might exist outside of the standard model. And as dark matter theorist Tim Tate of the University of California, Irvine, involved in the LHC Dark Matter Working Group, said in a CERN statement, the LHC has really broken new ground in the search for dark matter, in the form of weakly interacting massive particles. So far, the LHC has attempted to spot this dark matter candidate. Scientists have used the LHC to look for WIMPs by searching for signals of what might be created by, for example, WIMPs interacting with ordinary matter, Tice said. But all of the observed results have been consistent with models that don't include dark matter. However, the data so far gives us important information as to what kinds of particles can no longer explain dark matter. Even if WIMPs can't explain dark matter, chasing these particles has been fruitful. As Tate said, the results have both pointed experimentalists in new directions for how to search for dark matter and prompted theorists to rethink existing ideas for what dark matter could be, and in some cases, to come up with new ones. But the door isn't completely shut on WIMPs, and the mystery of what they may or may not be still hangs out there. As John Ellis, a particle physicist, said earlier this year, "I still hold a fire for WIMPs." Actions. Axions are another hypothetical elementary particle that have been in the spotlight as WIMPs have lost a bit of their luster in the scientific community. The axion, proposed in 1977, has both low mass and low energy. In 2020, physicists found the first direct evidence of axions and fanned the flames of interest in the particle as a dark matter candidate. Especially with the 2020 findings, the axion is growing in popularity as a dark matter candidate. But no one has yet caught an axion by directly detecting the particle in an accelerator like the LHC. In the words of Benjamin Safdie, an assistant professor of physics at the University of California, Berkeley, whose research includes investigating possible explanations for dark matter. It is a new particle we don't know about, and the axion could be that particle. It could be created in abundance in the Big Bang and be floating out there explaining observations that have been made in astrophysics. Scientists have proposed a number of possible experiments that could be used to try and catch an axion. But, as researchers described in a 2018 CERN statement, the LHC can be used to search for a new hypothetical particle, the QCD axion. Even though physicists haven't yet caught either the axion or this similar variety, it's possible that future experimentation with the LHC might shed new light on this particle mystery, potentially confirming scientists' suspicions about the axion or finding new information that changes existing ideas entirely. Ghost particles. Neutrinos, nicknamed ghost particles because of their elusive nature, were spotted for the first time in a particle accelerator in 2021. The discovery was made at the LHC and was a major breakthrough for physics that has opened up a whole world of subatomic mysteries. Neutrinos are subatomic particles similar to electrons with no electrical charge and such a small mass that scientists used to think they had no mass at all. Neutrinos are thought to be one of the most prevalent particles in the entire universe. Every second, about 100 billion neutrinos pass through every square centimeter of the human body, and these particles, produced in the hearts of stars through nuclear fusion, are just about everywhere. But because neutrinos don't interact much with matter, and because of their lack of charge and tiny mass, they have been remarkably difficult to spot in particle accelerators. LHC's landmark 2021 detection changed that, and with this big first accomplished, the LHC can now push this science forward, further exploring these ghostly particles that permeate our universe. Supersymmetry. Supersymmetry is a fundamental mystery of the universe that continues to lurk in the back of scientists' minds. Simply put, supersymmetry is a theory suggesting that all of the universe's fundamental particles should have counterpart theoretical superparticles. This theory, which is an extension of the Standard Model, says that when elementary particles, like photons or electrons, were formed at the beginning of the universe, they were created alongside matching superparticles. The theory suggests that every particle seen in the Standard Model has a partner particle that spins differently. However, there has been no concrete direct evidence of supersymmetry. Scientists hope that by using a facility like the LHC, as astrophysicist Paul Sutter has explained, scientists could essentially recreate the conditions of the early universe and search for signs of supersymmetry. CERN said in a statement that, if the theory is correct, supersymmetric particles should appear in collisions at the LHC. Scientists have previously wondered whether the LHC is creating supersymmetric particles that are escaping the detector then decaying. And since experiments at the LHC like ATLAS, the largest general-purpose experiment at the LHC, detect particles decay and the products of that decay rather than the particles directly, physicists remain concerned about how these particles could be detected if they are indeed there. But with this mystery lingering, it makes new opportunities for exploration with the LHC all the more exciting. The matter-antimatter problem. One of the biggest mysteries in science remains what is known as matter-antimatter asymmetry. As we understand it, the Big Bang should have created nearly equal amounts of matter and antimatter in the early universe. But the universe today appears to be primarily composed of matter, with very little antimatter. This mystery asks, what happened? Scientists believe that the Big Bang created a nearly equal amount of antimatter and matter because if there was the exact same amount, the two types would have essentially canceled one another out, leaving behind an empty universe. But that slight asymmetry between matter and antimatter at the Big Bang isn't fully explained by the Standard Model. And physicists are also unsure how this slight asymmetry led to the matter-dominated universe that we live in today. With the LHCb experiment, scientists have investigated slight differences between matter and antimatter. As told, earlier in 2022, the largest matter-antimatter asymmetry was observed with this experiment. Future investigation could reveal new details about why and how our universe came to be. Mystery particles. If the world's largest and most powerful particle accelerator is good at one thing, it's smashing particles together. This technology has enabled incredible steps forward in the field of particle physics, including creating and observing strange new particles that scientists had only suspected might exist. From 2011 to 2021, scientists using the LHC discovered 59 new types of hadron particles. Among those, in 2018, was a strange mystery particle. In 2021, a rare 4-quark tetraquark particle, a non-elementary particle, was spotted at the LHC. And of course, the Higgs boson discovery at the LHC certainly counts as a remarkable particle find. As researchers continue to smash protons near the speed of light and explore the fringes of what we know to be true about the universe, it's likely that strange new particles will continue to pop up during the LHC's new operational phase. Play sound. The Standard Model. The last item on this list is almost an honorable mention, but it remains one of the most significant, all-encompassing objectives that scientists use the LHC to investigate. The Standard Model describes all known forces and particles in the universe. It's the best theory of everything that scientists have to work with. But the Standard Model isn't complete, and as we explore major unknowns like dark matter and dark energy, researchers continue to explore how they might need to extend the Standard Model. The LHC allows scientists to both confirm what we already suspect about the Standard Model and also see where the model falls short, whether physicists may need to extend the theory or break the model apart altogether. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.